Alright, I know that the first thing you guys probably think of when you think of things that are buffer, you think of me, of course, but in this case we're not talking about that kind of buff. We're talking about buffers that resist a change in pH. So what a buffer is, it's some kind of solution or thing you add to a solution so that makes it, the pH will not change or will have very, very small amounts of change. So if you have a buffered solution, if you add a strong acid or a strong base, which means high dissociation, which means high numbers of H plus or OH minus, if you add them to the solution, either one of them, to the same solution, the changes in the pH are going to be very, very small. So if you were to add, a milliliter, 1 milliliter of NaOH to pure water, okay, whatever the concentration is, sodium hydroxide is a strong base. If you add it to water, the pH swing of the water is going to be very, very high. So it's going to drive the pH up very quickly, even a small amount of sodium hydroxide. If you do the same thing, add 1 milliliter of HCl to pure water, it's going to have a drastic swing on the pH. It's going to take it from 7 neutral and then drive it down, even with a small amount of HCl. However, if it's a buffer solution, if you add the same amount of sodium hydroxide and the same amount of HCl, it's going to resist the change in pH. Even if you have a buffer that's buffered to a pH of 7, so something that's buffered to a neutral pH, you add one of those to it, the pH will not change by that much. So it can kind of soak up those bases, those acids, to prevent shifts in pH. And buffers don't have to be pH to a neutral solution. You can actually pick your concentration or your pH that you want it to be. So like if you want a solution that needs to be buffered at a pH of 3, you can build a buffer, make a buffer that stays at a pH of 3, even if you add sodium hydroxide or cesium hydroxide, any of those strong bases, or a strong acid to the solution. The ingredients for making a buffer are one of these two choices, and this is important, so make sure you guys know these choices right here, because you're going to see several questions on the test that ask you about making a buffer. So a buffer is composed of either a weak acid or a weak base. You cannot have a strong acid or a strong base to make a buffer. So a weak acid, and if you use a weak acid, you're going to combine it with its salt, which generates extra conjugate base. Okay? So basically the overarching ingredients are weak acid and its conjugate base. So the conjugate base of a weak acid. Or a weak base with its conjugate acid. So weak acid, conjugate base, or weak base, conjugate acid. You're going to see lots of questions on the test where they'll say, hey, here's a couple choices, A, B, C, and D, and they'll tell you some acids and some conjugates and ask you which one will generate a buffer. And so they might tell you something like, all right, you've got HCl and Cl minus, will that make a buffer? Well, no, because HCl is a strong acid. But if you have something like acetic acid and sodium acetate, which would be a weak acid and its conjugate base, that would be a buffer. Let's actually look at that acetic acid system that I just mentioned. So acetic acid, CH3COOH, is going to be at equilibrium with H plus and CH3COO minus. So with a weak acid like acetic acid, it's going to lie mostly to the left. So equilibrium lies far to the left for a weak acid, which means we are going to have lots of this acetic acid undissociated left in the solution. Salts, on the other hand, completely dissociate. So if you were to take that sodium acetate that I mentioned, NaCHCOO, and put it in water, it's going to completely dissociate to Na plus and CH3COO minus. So when this completely dissociates, 100% ionization, that means we're going to generate lots of this conjugate base, the CH3COO minus from that guy. So what this means, in essence, is we're going to have lots of CH3COOH in the solution and lots of its conjugate base, the CH3COO minus. So what we're going to end up having then is a buffer, because we've got a weak acid and its conjugate base both in high amounts in the solution. What winds up happening then is, let's say we add some sodium hydroxide. So we add a strong base, NaOH, to the solution. Normally those hydroxides would come in, those OH minuses would drive up the OH minus concentration, so we'd wind up with a really high pH. If we add OH minus into this solution, well, it's going to react with those H pluses, and it's going to cancel it out and turn it into water. So what happens then when we lower the concentration of H pluses, because we just used some of them up, this CH3COOH is going to ionize some more, regenerate those H pluses that just came in to fill up that gap. So this would be Le Chatelier's principle. When we add the hydroxides, it will drive the equilibrium over, and so that's going to help reestablish the H plus concentration, and so pH would stay the same. Because we use up those OH minuses, and even though we may have canceled out an H plus, it's going to be regenerated by this weak acid. On the other hand, if we add HCl to the solution, HCl, so that's going to generate H pluses. Normally we would add that to a solution. Those H pluses would drive up the H plus concentration, which would drag down the pH. But when we add the H plus to this solution, hey, we've got lots of this weak acid, which is going to combine with that guy, generate the undissociated formic acid, or acetic acid, and cancel out that H plus. When that happens, so we're going to regenerate some of this CH3COO. It will dissociate some more to fill in that void, and we can end up soaking up, just with this whole thing, it's a sponge for OH minuses and H pluses. Now, eventually, you're going to run out of CH3COOH to dissociate. You're going to run out of this conjugate base from the salt that we put in there. But in the meantime, until those two sources run out, the pH will not shift by very much, because you've got something to soak up those hydroxides and H pluses. All right, so let's take a look at this same buffered situation. So we don't have to write them as separate reactions anymore. We know that there's going to be lots of the weak acid, and there's going to be lots of the conjugate base. So you've got a weak acid and its conjugate base in this solution. Now what if we wanted to figure out what the pH that this is buffered to? So like I said, buffered solutions aren't always buffered to a neutral. In fact, this one will not be neutral. So we're going to buffer it to a particular pH, and it depends upon the concentration of acetic acid and on the common ion that we have in there as well. So this is where that common ion thing comes into play. There's two things that are going to be changing the pH. The acetic acid and the conjugate base both have kind of counter effects on the pH. So where does the pH end up laying? So let's just do some fancy algebra then real quick to figure out the pH. So Ka is equal to the concentration of H plus, and in this case times acetate, CH3COO minus, divided by the concentration of the undissociated acid. So in order to figure out the pH, we need to look at the H plus concentration, because it's the negative log of the H plus concentration. So if we rearrange this equation so that it's H plus equal to the Ka times the concentration of CH3COO minus divided by the concentration of CH3COOH. Okay, so got that equation. I'm going to clear the screen and bring that equation up so we have some more room to play with it. Okay, here we go. Sorry, on the previous slide I think I messed up the equation a little bit. When we rearrange this, the CH3COOH, so the undissociated acetic acid, is going to be on top and the acetate will be on the bottom. If you don't believe me, do the algebra yourself, rearrange it, and this is what you're going to end up with when we have Ka over by itself. All right, and since we want to get the pH, that means we really need the negative log of the H plus concentration, but if we get the negative log of the H plus concentration, whatever we do to one side, we got to do to both sides. So we're going to have to end up negative logging everything on this equation. And that's okay. So if we take the negative log of anything, what we are getting is the P of anything. So if you take the negative log of H plus, you get the pH. If you take the negative log of OH, you get the POH. If you take the negative log of the Ka, what do you get? Why, you get the PaH. Ka. And that is a legitimate value. That's something that you talk about a lot, especially in organic chemistry. And when we take the negative log of the concentration of CH3COOH divided by the concentration of CH3COO minus, you just get the, oops, shouldn't have an equal sign there. Should be a times. You get the negative log of CH3COOH divided by, and those are concentrations, CH3COO minus. Isn't that beautiful, ladies and gentlemen? So what we have here is we can figure out the pH of a solution by taking the negative log of the Ka for that acid, multiplying it by the negative log of the CH3, so the concentration of the undissociated acid, divided by the concentration of its conjugate base. Then we can actually simplify this equation even more and write it as pH equals pKa. And one of the properties of logs, since logs are just exponents, is if we're multiplying two logs, it's the same as adding them. And since this is a negative log, that would make it subtracting them. So really we can write this as pKa minus the log of CH3COOH divided by the concentration of the acetate. But to simplify it yet even more and to get it so we're adding, we'll just take the log and we'll flip these values right here. So I'll just take the inverse. So CH3COO minus concentration divided by the CH3COO minus concentration. Okay, if that algebra right there scared you at all, it's not that big of a deal. You're not going to have to derive this equation ever again. On the AP test sheet, this is what you will see. Okay, this is the equation that you need to know and know how to use. I just showed you how it was derived in case you're curious. So pH equals the pKa plus the log of the concentration of the acetate. I'm sorry, that bottom one should be, so it's the concentration of the acetate divided by the concentration of the undissociated acid, CH3COOH. There is your equation. And when we turn it to more of a generic equation, so it's not dealing with just acetic acid and its conjugate, this equation right here is called the Henderson-Hasselbalch Equation. That's right, not only does it look cool, but it's got a pretty sweet name too. And there ends up being two ways to calculate the pH of a buffer. The first one is the method shown in the common ion effect that was back at the beginning when we looked at those. That one's a lot more tricky. You got to use ice tables, go through, okay, can we keep the minus x, can we keep the positive x, and all that jazz. The other option is the Henderson-Hasselbalch equation that I just showed you guys, and it's a little bit easier. Okay, you've got to know what to plug into where, so it's not quite as thought out as the other one. So it's a lot easier to make mistakes with the Henderson-Hasselbalch equation because you can put the numbers in the wrong place pretty easily. Whereas with the common ion effect method, you can kind of lay out the process very, very cleanly for yourself, and so it's harder to make a mistake that way. But we'll go through the Henderson-Hasselbalch and just practice that a little bit. So the Henderson-Hasselbalch equation in generic terms, looks like this. So you can have it in two forms. You can have it for the pH or the pOH, depending on what kind of system you're talking about. So if you have a weak acid and its conjugate base, you would use this form because it's a weak acid. If you have a weak base and its conjugate acid, you would use this form. And to convert it to pH, it's just pH plus pOH equals 14 as usual. Okay, the pKa and pKb, they're the same thing. It's just the negative log of Ka or Kb. The A minus that we see right here, that is the molarity of the conjugate base. So when you add that salt, like the sodium acetate, it would be the concentration of that salt that you added. The HA, the number on the bottom, that would be the molarity of the weak acid, so the initial molarity. So this would be the molarity of your sodium acetate. This would be the molarity of your acetic acid. So conjugate base, weak acid. Over on the basic version, the weak base version, the HB plus, that represents the molarity of the conjugate acid, so that's the concentration of the salt that you added. The B on the bottom, that's the molarity of the weak base, so the initial molarity. So on either one of these, the bottom number would be the weak acid or the weak base, and the number on top would be the conjugate acid, or the conjugate base, or the conjugate acid. And it should make sense to use the A minus, that would be a conjugate base because it's wanting to accept those protons, and the HB plus, that would be a conjugate acid because it's wanting to donate that extra positive proton. And then the bottom numbers are just the undissociated versions. Okay. So here are these equations. Both of them are actually given to you on the AP sheet. It's just a matter of recognizing what gets plugged into where and how to calculate it. So these two numbers right there, making sure you don't flip them, is one of the biggest challenges. Let's take a look at an example. So find the pH of a buffered solution created by mixing 0.15 moles of ammonium nitrate with 0.65 liters of a 0.25 molar ammonia solution. Let's assume that the volume change is negligible. So that means the volume at the end is going to wind up still being 0.65 liters. Let's look at the equations at play here. So ammonia solution, NH3. That's going to be mixed in with water, and that's going to generate NH4 plus and OH minus, and that's at equilibrium because that is a weak base. And then the ammonium nitrate, okay, that's 100% dissociation because it's a salt, NH4 plus and nitrate. Cool, so here we got our weak base, the NH3. Here we've got our conjugate acid, our NH4+. So both of those are in this solution, which means we can solve this pretty easily using the Henderson-Hasselbalch equation. So I'm going to go to a fresh page so we can work out this problem, hopefully in one place. But oops. We do have our salt right there, and we have 0.15 moles of it. And so remember, for the Henderson-Hasselbalch equation, we're going to need to know the concentration of the conjugate acid that we've added. So let's do that first. If we have 0.15 moles and 0.65 liters, what's the concentration of our NH in the solution going to be, or NH4? So the molarity would be the 0.15 moles of ammonium, in a 0.65 liter solution. So that means the concentration of NH4 plus is going to be 0.23 molar NH4 plus. Great, and let's look back at the Henderson-Hasselbalch equation. POH is the pKa plus the concentration of HB, so HB would be the NH4 plus concentration. Okay, so the conjugate acid goes on top, and then on bottom would be the concentration of the weak base, in this case, the NH3. And this is, sorry, the negative log of those concentrations. Make that just the log of those concentrations. So POH equals the pKa plus the log of the concentrations of ammonium divided by the concentration of ammonia. So there's our conjugate acid, there's our weak base. So if we plug in numbers to solve for the POH, POH would equal the negative log of the Ka, and the Ka is 1.8 times 10 to the negative fifth. We're going to add that to the log of the concentration of NH4, which we found to be 0.23 molar, and the concentration of the weak base, which was 0.25 molar. And when we solve this out, we get a POH of 4.71. But the question asked us for the pH, and pH then would be 14 minus 4.71, which means that the pH is going to equal 9.29. So this solution then would be buffered to 9.29. That means if you add some strong acid or some strong base, it will absorb that strong acid or strong base and have a negligible effect on that pH. So if you add base to it, it might raise it, 9.291. Okay, so a slight change in pH, but nothing noticeable. Until eventually it ran out of those buffering capabilities, it couldn't absorb those hydroxides anymore, then it would start to raise the pH. Same thing if you were to add a strong acid to it. At first it would have maybe a small drop in the pH value, but very, very negligible, nothing you would really pick up until it ran out of those buffering capabilities, and then the pH would start to drop. So it's going to stay buffered at 9.29 for as long as it can. Alright, so let's take a look at what would happen when we added this some hydrochloric acid, so some strong acid, to this buffer system that we created in the previous problem. When we do this, we're going to assume the volume doesn't change. We've got a liter of it, so the small amount that we're going to add isn't going to adjust the volume and affect concentrations. So we'll be adding H pluses to the solution, and the H pluses are going to react with the ammonia that's in the buffer, so the NH3 will react with the H pluses to form that NH4 plus. And to figure out how this interaction is going to go down, let's make ourselves an ice table. Alright, so the NH3, we initially had 0.25 moles, so it's a 1 liter solution, so it's 0.25 molar, then it's 0.25 moles. And then we add 0.02 moles of H plus. And we're starting with 0.23 of the ammonium. So then what happens with the addition of this 0.02 of H plus, that's going to react with this NH3, so those two are going to combine to form more ammonium. So that means that NH3 is going to have to decrease by 0.02 because the 0.02 of this is also going to decrease, and we're going to form another 0.02. Sorry, that looks really weird. So another 0.02 of the ammonium. So then at equilibrium we'd be left with 0.23 and 0, and this would increase to 0.25. So the addition of the H pluses reacted some of this ammonia to bring the concentration of ammonia down to 0.23 and the concentration of ammonium up to 0.25. So that's going to adjust the concentrations that go into the Bronsted-Lowry, which is that the POH in this case, which is the pKb plus the concentration of NH4 plus divided by the concentration of NH3. So what we've done then is initially in this problem we used this as our concentration of NH3 and this is our concentration of ammonium, but now those have changed. Now it's 0.23 of ammonia and 0.25 of ammonium. So that's going to change, in essence, our POH and our pH. Okay, so to find our new POH, we're going to plug those numbers in. So the pKb would be the negative log of the Kb, which is still 1.8 times 10 to the negative fifth. And we're going to add that to the log of the new concentrations, which would be 0.25 on top and 0.23 on the bottom. Both of those would be molarity. And that gives us a POH of 4.78. And if we get the pH as 14 minus 4.78, we find out that the pH is 9.22. And initially the pH would have been, it was 9.29. So that means with this buffer we added a strong acid and we added 0.02 moles of it, so that is a significant amount of moles. It only changed the pH by 0.07, so it's not a huge shift in pH. So the system was an effective buffer. Right now if we just take a little bit of time to kind of analyze the Bronsted-Lowry equation, the Henderson-Hasselbalch equation, and look at how it works and just what it shows us about buffers. So if the pH equals the pKa, that can occur. So if we're trying to achieve a certain pH, we can just look at the pKa's of different acids, but we have to have the same concentration of the salt and the weak acid or weak base if we're looking for POH. Because if we have A minus equal to HA, those two are divided by each other, which would give you a value of 1, same number on top and bottom, and the log of 1 is 0. So the Henderson-Hasselbalch equation, pH equals pKa plus 0. And so the pH would just wind up being whatever the pKa is. The second point, buffers made from very weak acids and their salts have high pH values. So remember, weak acids produce stronger conjugate bases. They don't produce strong conjugate bases, they produce stronger conjugate bases. So since they have stronger conjugate bases, that would be their salt, the stronger conjugate bases would increase the OH minus concentration. And then by counterspect, if you want to produce a lower pH, if you want to produce a more acidic pH for a buffer, you would want to use a stronger weak acid. You have to use weak acids and not a strong acid, just a stronger one of the weak acids, because its salt will be a slightly weaker version of the base, so it's not going to increase the OH minus. It's not going to hydrolyze water the same way a basic anion, a strong basic anion would. So you wind up with a higher concentration of H plus in there. And then what they're doing here with these examples that they're giving, so they're saying when the pH equals the pKa, so in both of these examples we're saying, all right, we're using the same concentration of the anion and the conjugate salt, or the salt and the weak acid. So if you have something with a very, very low Ka value, that means a very, very weak acid, and pH equals pKa, so its Ka value for a weak acid would be something like 1 times 10 to the negative 10th. The P of that would be 10. So you see you get a higher pH for this guy. In fact, it ends up being a basic pH, even though we're dealing with a weak acid, because it's got that strong conjugate. On the other hand, if we once again set the concentrations of those two equal for our acid and our salt, and we have a slightly stronger weak acid, so 1 times 10 to the negative 4th as opposed to times 10 to the negative 10th. Negative log of that gives us a pH of 4. So we do wind up with a much lower pH as is buffered to an acidic solution. All right, here's an example of a question number 4 problem. So hydrobromic acid is added to a buffered solution containing acetic acid and its salt. So the buffer system that we have set up here would be CH3COOH, and that would be at equilibrium with H plus CH3COO minus. And we have added extra of its salt, so what we're saying then is at equilibrium we have lots of the weak acid and lots of its conjugate base. So then this particular question, so this is just a buffer that's set up in the system. For this particular question we have hydrobromic acid, which is a strong acid, so that means we're just going to be dealing with those H plus ions. And so the question for us then is, who's that H plus going to react with in this buffer right here? Is it going to react with the acetate? No, because there's nothing for it to stick to. Is it going to react to the H plus? No, they're both positive. Yeah, that's right, it's this guy. So since there's lots of this, unlike just a weak acid and a strong base reaction, or a weak acid and something else, it's not going to be breaking apart this guy. It's going to be dealing with just this guy right here, because it's got the negative charge. So that means our net ionic equation for this one would be CH3COO minus plus H plus yields us that acetic acid again. Okay, so the H plus is going to be reacting with our CHO3 minus to drive it backwards. And that's also what buffers the system, because we've got lots of this, and so it absorbs that H plus and turns it into the CH3COOH, which even though this is an acid, this does not contribute to the pH because the H is attached to it, so it's not going to affect the concentration of the H pluses. Okay, that's it. You now know about buffered solutions. This is going to become real important that you know how to do calculations with these. You recognize how to make certain buffered pHs, that you know what happens when you add a particular ion to a buffered solution, how to calculate what the concentration is, what compounds make a good acid or buffer. But where this is going to be really important is next when we talk about acid-base titrations. Buffered solutions end up happening when you do a titration with a weak acid or a weak base. So it's going to be really important that you know how to use the Henderson-Hasselbalch equation. So give it some practice, ask some questions, and hopefully we can get those titrations down pretty easy.